execution time alone tells us nothing. Clock speeds and hardware are transient illusions. To truly understand the nature of computation, we must analyze the structural growth of algorithms. The Master Theorem acts as the ultimate lens for resolving the tension between recursive expansion and local processing.
Before we build the theorem, we need a foundational model. We use the Abstract Random Access Machine, or RAM. Here, basic arithmetic and logic execute in constant theta-1 time. This allows us to neatly define the cost of local algorithmic work without worrying about low-level hardware bit complexity.
The Master Theorem strictly models the divide-and-conquer paradigm. Imagine a highly efficient factory. First, you divide a massive task into smaller, self-similar chunks. Second, you conquer them recursively. Finally, you combine the subassemblies into a finished product. Mathematically, this execution flow is expressed as T of n equals A times T of n over B plus F of n.
Think of algorithmic recursion as a massive growing tree. The variable A dictates how wide the branches split, while B determines how quickly those branches shrink toward the base case. The true battle of computational efficiency is a tug-of-war between the watershed function, representing the proliferation of leaves, and the driving function, f of n, which represents the work done at each individual node.
In regime 1, the recursion tree is intensely leaf-heavy. The cost of splitting and combining is cheap, but the sheer volume of subproblems is overwhelming. The total runtime is asymptotically bottlenecked by the number of leaves. For example, if a manager delegates tasks instantly, but the thousands of frontline workers take all the time, the frontline determines the speed. Local optimizations at the top are mathematically useless here. Regime 2 is the sweet spot. Here, the local work required to divide and combine the problem grows at the exact same rate as the proliferation of subproblems. The computational mass is perfectly balanced across every level of the tree. This is the domain of merge sort, resulting in an additional logarithmic multiplier that represents the total height of the tree. In regime 3, the recursion is root-heavy. The overhead of dividing and combining completely eclipses the cost of solving the subproblems. To guarantee this, we apply a regularity condition, stating that A times f of n over b must be less than or equal to c times f of n. Crucially, the constant c must be strictly less than 1. This ensures the work decays geometrically as we move down the tree, making the recursive calls asymptotically negligible compared to the root. Let us apply this cookbook to reality. Merge sort sits at perfect equilibrium, balancing linear merge costs with recursive splits. Binary search follows the same equilibrium on a single path. Strawson's matrix multiplication is a prime example of a case 1 win. By reducing the branching factor from 8 subproblems to 7, it lowered the watershed exponent and shattered the standard cubic time barrier.
The standard Master Theorem requires a strict polynomial difference, separated by a factor of n to the power of epsilon. However, logarithmic variations do not create unsolvable gaps. For instance, if the local work grows slightly faster than the watershed by a log factor, we simply use the extended Master Theorem. These tools bridge the functional gaps that the basic cases cannot handle on their own. When the standard cookbook encounters unbalanced recursive hierarchies, we turn to the Akra-Bazzi method. It proves that discrete recurrences with unequal subproblems have a hidden continuous underlying structure. By abandoning discrete algebraic summation in favor of continuous integral calculus, we resolve the chaotic geometry of complex algorithmic trees into absolute mathematical certainty.